All right, welcome back, guys. In this lesson here, we're going to discuss how to solve word problems involving system of two linear equations. In the previous lesson, we learned how to solve those systems using the two methods, substitution and elimination. In this lesson, the problems will be given written in a word format, and it's our job to read it and extract the correct information, and then write the system of two equations that pertain to the problem. I think that's probably the most difficult part. Once we have the correct setup, the rest is just doing the algebra to get the correct answer. So I only got two examples I want to go over this video here. So the first example is referring to, so let's go ahead and read that. Suppose you want to blend two teas to obtain 10 pounds of new blended tea, which sell for $350 per pound. Now TA sells $4 per pound, and the TB sell $2.75 per pound. And we're also assuming that the revenue selling the new blended tea and from selling the tea separately will be the same. Okay, and we want to determine. So it says determine the number of pounds of each tea required for this blend. Okay, so if you read first time, it doesn't make sense, you read again, and you can just extract word per word, sentence per sentence. So you see a bunch of numbers. What you don't want is you don't want to write these numbers down, do some math, and get the right, hopefully get the right answer. It doesn't work that way. So just try to read more into it and see if you can understand, just sentence per sentence. So if we go back to the first sentence again, it says, suppose you want to blend two teas to obtain 10 pounds of the new blended tea, which sell $3.50 per pound. So if I was to rewrite this or kind of paraphrase this or write this in my own word, I usually draw a picture. It helps a little bit. So here's my picture. All right, so I got two type teas that I want to mix or blend them, and I want to get 10 pounds of the new tea. So 10 pounds of the new tea. I want to this is TA, the first type T. This is TB, and then I want to mix these two. Okay, and when I mix them, I create this new tea. I want to sell that at $3.50 per pound. Okay, and we also given that the TA is sell at $4 per pound, and then TB it sells at $2.75. Okay, so far we want to mix two tea. We want to get total. So call this new blended or TC. We want the 10 pounds total of the new blend, and we we don't know how many. We're supposed to determine how many pounds of TA, how many pounds of TB that we want to mix together, so that way you get 10 pounds of the new tea. So suppose we don't know how many pounds per for TA and TB. Let's call this X, and let's call this Y, right? So X be the number of pounds for TA that we use in this mix, and then Y be the number of pounds that we need to use for TB. Okay, we do know that we want it to come out to have a total of 10 pounds of the new blended tea. So the total or the sum of X plus Y should equal to 10, and that's what this first part is saying here. There's one more information that we're supposed to extract, and that is this here. It's assuming that the revenue from selling the new blended and from selling these teas separately will be the same. So revenue, if you recall, revenue is equal to how much per pound times how many pounds is selling. So we call that quantity. So that's how we calculate revenue. Okay, so we do know that, okay, for the new blended tea, the revenue of that is 350 times 10. That's the total number of pounds that we're gonna sell. Is $35, and then we do know that the revenue for T and TB is calculated at 4 times X plus 275 times y. Okay, so we want to calculate this revenue so that it's equal to the revenue of selling the new tea. Okay, so that's the information we're given, the revenue information, and also the quantity, which is the number of pounds we use for this mix. Okay, so we got two equations that we can put together. Equation 1, and then equation 2 is going to be the revenue equation. Okay, so I'm going to go ahead and rewrite this as a system of linear equation. X plus y equal to 10. 4x plus 275, y equal to 35. This is the revenue. This is the revenue equation. This is the quantity equation there. And then now we can solve the system equation using elimination or substitution. So I'm going to go ahead and do it by elimination. So times by -4. So that will give me -4x plus -4x minus 4y equal to -40. Add it to this second equation, 4x plus 2.75 equal to 35. So that will give me negative 1.25y equal to -5, and then divide negative 1.25 into 5. That will give us 4 pounds for the TB, and then TA should be 6 pounds, and that should be your answer there. All right, 4 pounds of TB and 6 pounds of TB for this mix. Oh, TA, sorry. All right. So sometimes having a diagram helps quite a bit. Just kind of see what the big picture or see what the problem is really saying. In the next example, I'm going to draw a similar diagram or a table. Okay, so this deal with speed, distance, and time. It's saying that Cody's motorboat took 3 hours to make a trip downstream with a 6 miles per hour current. The return trip against the current took 5 hours. We want to find the speed of the boat in still water. Okay, so here's what we asked to find. Okay, and we're given that it took 3 hours to make a downstream trip with this speed of the current, and then the return trip is against the current took 5 hours. So there's a couple math words here that you might want to get familiar with, and that is downstream. Downstream against the current, that's gonna be upstream. Speed of the boat in still water. So there's several things that's not as clear we want it to be. Okay, so with this type of problem, first thing you want to realize is, okay, there's speed, there's time, there's distance. So the formula I'm going to go by is distance equal to rate times time. Okay, all right, so let's go ahead and draw a picture here or a diagram. So I'm going to have D, which is distance, rate, which is speed, and then time. Okay, all right. Okay, I'm gonna have this would be upstream. Let's go downstream first. Sorry, downstream, and this would be upstream. Okay, those are 2 trips there. Do we know how long is each trip here? We don't know. Okay, question mark. We do know the time for each trip, 3 hours for downstream and then 5 hours for upstream. Okay. So when you solving problems that deal with upstream or downstream, there is this thing called speed of the current is involved because you're on the river. It's not just smooth out there. There's always current in a different part of the river. In this case, we make things simple by assuming the current is constant throughout the entire river. So you want to consider the speed of the current when you do this here. So speed of the current is 6 miles per hour. Okay. So as far as the rate goes, when you go downstream, the word downstream means with the current, meaning you are going in the same direction as the rate or the flow of the water. Okay. So essentially, you are going faster than what you intend to go because the river, the flow of the river is carrying you downstream. So in that sense, there, you want to add the speed of the current, and then when you go against the current, which is called upstream, so this is against the current, and then this is with the current. Okay. So when you go against the current, the flow of the water is pushing against you, meaning it's making you go slower when you're in the water and when you're in this situation. So the motorboat will go slower than what is actually intended to go. So you want to subtract the speed of the current. Okay. So we don't know what the speed of the boat in still water is, so we're gonna call that x. Okay. So our x is gonna be the speed of the boat in still water. Okay. So what that means is whatever the speed it shows on the speedometer. So that will be, what you intend to go versus the situation where you go against or with the current. So we got this set up now. Okay. Notice that distance still question mark because we don't know how long is the strip, how far is the strip. But when we apply the formula, distance equal to rate times time. Okay, so we have the downstream trip is going to be d equal to x plus 6 times 3. And then the upstream trip is x minus 6 times 5. Well, both of the trips are the same trip. So we can assume that the distance is the same. Same trip, same distance, equal distance. So we can set these two equations equal to each other because they're the same distance, right? Same distance. So I'm going to say x plus 6 times 3 equal to x minus 6 times 5. And I'm going to solve for x. Distribute the 3, we get 3x plus 18, 5x minus 30. Subtract the 5x to the left-hand side, minus 18 to the other side. So that will give us 22 miles per hour. So that is the speed of the boat. So the speed of the boat in still water is 22 miles per hour. Okay. So if this is how fast you intend to go, both directions while you are going upstream and downstream. Downstream, say going 22 miles per hour, your boat will be traveling 28 miles per hour because the current is pushing you. And if you go against the current, then the speed of the boat would be 16 miles per hour because the current is pushing against you. But in reality, on your speedometer, it's saying that, hey, you have the boat going at 22 miles per hour. Okay. All right.